Thank you, Maria. Good afternoon, everybody. It's really my pleasure to be here to share our work on application geospatial and innovation in digital transformation in agro-food system. Just as Maria said, so I really want to show geospatial technology is quite useful, especially in food and agriculture sector. So I think that's one of my purpose here to present you. So this is the outline of my presentation. Some words on the background. So actually, food and agriculture is relevant to everybody, and it's much larger than you imagined. So that's the first part. And then two case studies. One is on cropland agreement analysis. Another one is leaf area index data product validation. A little bit technical. And then I introduced two platforms. One is FEO Essential Remote Sensing Data Product Portal, and another one is a big data platform called FEO Agro-informatics platform. And then there are a lot of materials of other geospatial applications in FEO. Then some words closest speech. Okay, first, agriculture is really important. It is a foundation for society and economic, social prosperity, but it's also bring impact on our environment. So according to various studies, so roughly half of land surface has been or is still used for agriculture. That's a huge amount. It's virtually any piece of land, if it's not too dry, if it's not too cold, if it's not covered by the rainforest, virtually most part of used by agriculture. That's information. And also, water is very important for agriculture. If we have water, we can have agriculture. But the bad news is 2/3 of the world population is suffering water stress condition right now, and that's also for agriculture. And another aspect of is the population. The population is growing, and according to the recent FAO report, about 9% of the world population, 780 million people, is in hunger. But the population is still growing, and just as I showed in the first slide, so the land for agriculture is quite limited, it's shrinking. So the pressure on agriculture is really, really huge. And also, I have this slide to show you before I use the data from US, but we have the same Chen if you use data for other country. Before 1930s, so the yield, this one shows the yield for maize. Before 1930, so the yield was quite stable, low and stable. Then we underwent three major agricultural revolution. The first one occurs in 1940s, 1950s, to the using of fertilizer, and then we have the green revolution to use some high quality braided crop seeds, and the yield increased a lot. And after 1980 and 1990, and in the first decade of 21st century, so this is a year for the genetic engineering. So we have this GMO and other varieties, the yield improved again. But in the last decade, it seems the trend stopped. We reached kind of plateau, period plateau. So that's something challenging. But we know by various models and also by practice, we have great potentials. For example, in FEO have GEZ, Global Agricultural Zones. So we know there are huge potential. Maybe we can increase the yield by 2 times, 3 times. But people don't believe that. It's just in theory. I just want to show some good news from the practice. So each year there's a yield contest in the U.S. for different crops. I just showed the result for maize in 2023. So the winner, so they use various methods to optimize the food the yield, including use the best seeds to fertilize the right amount, right time, and to optimize irrigation and pest management and tillage and so on. So the final winner, they reached a history record is more than 600 bushel per acre. But in contrast, the national average is just 180. So you can see there's a huge gap there. So we take the opportunity. So why I share this? Because agriculture is really from the parcel of cropland to region, to continent, to global. It's really heterogeneous. Either the condition, for example, the soil, the climate, and also the practice, and also the final yield varies from site to site geospatially. So in this way, geospatial is quite useful. That's why we use a lot of geospatial technology in agriculture to promote production and reduce the uncertainty of food production and food insecurity. Okay, so another concept I really want to share with you. So I said at the beginning, everybody is relevant to food and agriculture. So, and if you also realize that from the year 2020, we use a new term of agro-food system. It's not just agriculture and the food. It is a system. We involve the whole process of food production, storage, aggregation, post-harvesting and handling, transportation, processing, distribution, marketing, disposal, and consumption. This is really the whole process. And also, agriculture is not only for food. It's also provide fiber and other materials for our society. So it's really huge system. Everybody is relevant. And also, in terms of value, if you consider in the agro-food system, it's the number one manufacturer sector in the world. And also, it is through the supply chain. So many years ago, I had a talk with a professor from Germany. Germany is known as an industrial country. Agriculture itself, food production, only contribute 2 to 3% of the GDP. But if we can consider all this supply chain, including machinery, fertilizer, and so on, so that proportion for agri-food system could be as high as more than 30%. That's really high. But if you consider other countries like Italy, France, Spain, or even United States, the percentage is much higher. That's why it is very important. And also, just as I said at the beginning, geospatial is fundamental, necessary in agriculture management from parcel to the globe. Okay, that's the background, and then 2 case studies. We start from very simple one. So it's a good global crop analysis. Before we started this work, we thought this could be very simple one. Professor Borelli have a lot of work on that cover, and also Polytechnic is very good at that. And a lot of people is engaged in this area. Right now, we have, I think, more than 10 global land cover products. So we choose 7 of them to compare. But we found, cropland it seems a very simple part, but we found it is not that easy. So different authors, different producers of the global land cover, they use different definition. So and none of them is agrees to FEO definition. By the way, FEO have the FEO static database. FEOstat is widely used in a lot of research and applications related to agriculture, like food production and also global change. So how we can do that? So that's analysis. For all this land cover data, they use 10 power cropland. That means there's a new crop like maize, wheat, rice, and so on. And some of them include woody crop. In Italy, we have the olive trees. That's a very important crop for Italy and Europe. And also pasture and fallow land. Fallow is commonly used agricultural practice. It's an integral part for agricultural production. And also in recent years, greenhouses is intensive agricultural practice. So you can say there's no a single global land cover data cover all this sub category of cropland. So FEOstat is only tabular data. So they're only the static data for country or sub-regional regions. So if you want to do that for geospatial model, so that's a very fundamental data set we should have. And then we start the work. Then we calculate the disagreement between different data sets. We use two methods. The first is, we just make we calculate the map layers where for the same pixel where is cropland, where is not, and the second one we composite these 7 crop land cover layers in one 8-bit grid data. So we for each pixel we have the value from 0 to 127. So the result you can see the left we use the simple crop agreement method. The purple color means all these 7 products assign that pixel as cropland. The blue one is only one. So you can find there are a lot of disagreement, especially in Africa, Southeast Asia, Latin America, and also some part of Europe. So the right map shows use a detailed cropland agreement. So that it tells the same story. Okay, and then we make the validation. First, we collect the samples. So right now we are using the definition of temperature crops from FEOstat, and we use Google search engines, Google Earth to collect the map, and we do this sample collection with two methods, and we do the second check. After we have done the first one, we make the second round check with FEO2 collectors. So in total, we have 30,000 samples around the world. So that's the distribution among different regions. And then the validated sample generates a stratified random sampling based agreement map of the world zero and the watercolor because their resolution is high, and also it's the most recent one. So that's what have we done for collect. This show the process. We plot the sample on Google Earth, and then we link that to Google Earth engine. So to have the NDVI time series data for the interpreter to understand where is the temporary cropland, where is not. And then the sample to validate the accuracy of the cropland for each land cover data site. And this the first round. The second round is FU2 collectors. So there are different data there. So we make sure the sample accuracy is high enough to do the quality check. And this preliminary result, the first conclusion is among the 7 land cover products. So what survey has the most best accuracy for cropland? So if you just check the bright right stick on this chart, you can find the conclusion. And we harmonize the products to integrate also the 7 global land cover data together. Have this CAM7. It has the highest hour accuracy for cropland among the 8 products, and also it has higher cropland precision and non-cropland recall. So the result is good, but this is only for temporary cropland. So we will continue work for other categories. Okay. And though this to check to analyze the accuracy at global scale, we also done that for region scale. We use ecoregions. For each ecoregion, is the agricultural production conditions relatively homogeneous. So we choose 2 of these examples. One is in North Africa, another one in South Asia. So it tells the same story. All results have the highest overall accuracy, and also we plotted, we compared with FL stat, and so that's the result. So you can have details on the slide because Leo says the slides are already shared with you. We can say that what area is expected for crop, so they have very high accuracy for R square, and the CAM7 is also very high. This is the first case study, and the second one I will go through the leaf area index, Y leaf area index. So first, what is leaf area index? Simply, you can think itself. If we in a unit area, we pick all the leaves of the plant of the vegetation, and we project versus the unit area. You know, we can have a non-unit figure. That's the leaf area index. So we consider the both sides of the leaf. So you know that's the definition of leaf area index. But why it is useful? It is a key indicator for the vegetation presence and also vigor. And it is not. It is very important for plant growth, crop production, and so on. But it's also very important for water, for energy balance, and so on. This is not only for agriculture, but also for other research studies. So this really essential fundamental parameter widely used in a lot of sectors, including agriculture. And the methodology for inversion of the IOI. So we have a different category measure. The most simple one is ampere transfer function. So in this category, there are also a lot of different methods. And the second one is more physically physics strict inverse model. So and this is also widely used. But these two methods mainly based on the optical multiple band data. And there are another two categories use LiDAR and macro data for the inversion. So, but for the global data sites mainly use the PRES2 method. But for forestry, for forest, a lot of LiDAR is used globally. And like the land cover data, there are also a lot of LAI data products with different spatial resolution and temporal resolution. And for the validation, so this little this quantitative inverse parameter, so like classification, the validation a little bit complicated than land cover. So there are different scams for the validation. The first one is just the direct field to satellite AI comparison. Where we can mirror the AI in the field and compare directly with satellite inverse AI. But there are some shortcomings. There are obvious shortcomings for this method because there's a scale effect. That means in ecosystem at different scale, there are emergent feature after between different scale. And then we have the second scam. We add a second layer. So we put the high resolution geospatial data there for AI, and then compare with the satellite inverse AI. So make sure we consider the scale effect. And the scheme 3, I just introduced in the first slide, we have different, the IOI data, IOI invert can use different types of remote data. So we make comparison between multiple data products. And the fourth scam, so it's not just IOI itself, we consider relevant parameters like FPAR, and also climate environment parameters like temperature and other variables. So it's, and the fifth scam is we incorporate a model, simulate model into the comparison. And the last one is something to integrate the process-based model. It's kind of data simulation. But there, at a global scale, most people are using the second scam, to consider the scale effect. So we also use the second one. Just to let you know, there are various methodologies. The difficulty for LAI validation is that we don't have globally available data size for validation. So the first step for us is to collect the reference data. So there are a lot of large ground truth campaigns around the world. We just collect some of them, including imaging eyes, malaria, Bigfoot, and wild AL crop and CNERN. So they have a lot of, but they cover different region, different time frame. So this one just shows example how the data what the data look like. So there is the sample region usually is cover several square kilometers, and then they have the field measurement, and remote sensing images at different resolution. And then we because the different campaigns they have different standard data format, scale factor, and so on. So if we want to set up the reference data, we must standardize all this data and products. So that's the process we use. So we collect the data and upload to Google Cloud and to build up the lookup table, and then to standardize all the price. And then we have this reference data set for validation. That's our data product. So right now we are trying to make it available to the users, and also inspired by Professor Bradley's idea when we doing together with the GeoAI challenge. So we want to make this open for the users to validate their data products. And even after a certain time, we can do a benchmarking for the algorithms or for the data size for GeoAI. This the first version of our reference data set distribution. You can say it's not too many, but that's the reality. But we are doing more efforts to make more data available. And based on that, we have done the preliminary analysis of some existing GeoAI global data products. So we choose some size here. And that's the methodology. It's roughly the second scan for GeoAI validation I shared in the prior slides. And this is the result. This side is in Spain. So we compare 3 data sets. One is Modis GeoAI, and the second one is Glass GeoAI. It's generated by Hong Kong University and the University of Maryland. And probably GeoAI is a European data product. So we can find in this side. So all of them is not so good, but relatively the glass one is better. And this another side. So the result itself is not so important. So we make this available. Users can make the validation by themselves. And okay, this is for Ukraine. So and also, yeah, this we put all the case study for Modis in the same graph here. This for glass. This for property. Yeah. Okay. This table. I don't want to go to details of that. So the idea is, the next step for us, we based on this evaluation, so we will do something similar to the cropland to generate a relatively higher accuracy GeoAI data ready to be used by users who are not interested in the quantitative remote sensing or parameter inversion. They only want to do some follow-up work, either for crop analysis or for environment analysis. Okay, we are doing something quite similar for ET, river transportation. So we just started work. The methodology is quite similar as I introduced in the previous session. And based on that, we developed this essential remote sensing data portal. So the idea is, we want to share this with standardized, follow interoperable data sets ready to be used by users who are doing research or application right into food and agricultural environment. So we have not officially launched the portal. So, but there's a link you can have a look. and you're welcome to give us feedback on that. There's a process. So we have data layer, application, and pre-digital layer. So the main tool we use Disk Manager and Stack. And this is the function. Then is data catalog, data search, and support data download. And the second platform is FEO Agri-informatics platform. So in FEO we cover really a lot, many sub-disciplines relevant to food and agriculture. Especially after we endorsed the concept agri-food system, is to cover really a lot of area. And in the year 2019, we start a hand-in-hand initiative to promote implemented SDGs for food production and eliminate hunger. So this really a large platform is cloud-based and standard-driven. And these are all the slides. So right now we have more than 2 million data layers and more than 20,000 users and a lot of data download and usage. So this platform not only archive raster and record data, but also tabular data. So it's support flat attribute list and also multi-dimension data queue. It archive not only observed data, but also calculate model data there. And the structure of the platform. We didn't start the work from zero. We based on the rich FEO platforms, and we use the federation methodology, and to have very good data cataloging and supportive data realization. And also we call the agri-informatics platforms not only data. We also incorporate knowledge and analytic tools and models there to support users for various applications. There's a catalog metadata. This plan is open to everybody. You don't need a registration. So there's a link you can play there, and also you're welcome to give us feedback. If you need some data, you're free to download, and if you need some new one, please tell us. Maybe we can generate if agree to our regulation. And there is a lot of applications, and also this integrate raster, raster vector and the tabular data together for very complicated analysis. I just list some use cases here, and I just want to highlight, it's intensively used for FEO initiative and the project programs. For example, for the hand-in-hand initiative to promote food production in the food insecurity regions. So this tool used for gap and potential analysis for these countries to attract the investment. So this one already applied in more than 40 countries. Until last year, we have them attract the investment more than $21 billion and the benefit more than 156 million people there. So in this way, this technology is really useful. This is at global country scale, but at the local scale, part with technology compared with precision farming is also quite useful. And at the beginning I said, water is critical agriculture. We support that this platform to water counting, and also we have the mobile apps to transfer the knowledge, action, information to the farmers and guide their practice. And besides that, we have a lot of applications, including we add just a list here. So including water, stress, and also forest, disease and health, pests, a lot of things. A very interesting part, we also integrate social media data with the geospatial technology to make the sentimental analysis for food security and food waste. So I will not go through for the slides follow, so you can have a look. If you have any question, you can email me. And just a final conclusion. So we have a lot of applications in agriculture. So we just show the example in a few. If you review the literature, so there's massive applications. And I just want to highlight, in past we do a lot of this classification, but I think in the future there are a lot of quantitative remote sensing will be used. And I think FEO is one of the pioneer in this, the very famous LCCS. Actually, is efforts to try to integrate classification and quantitative remote sensing. And also, I just showed that some example. So we should integrate data and knowledge together to make geospatial more useful in agriculture sector.